All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Hugo Hernault. He is a senior data scientist at Playtika, Switzerland. Please join me in welcoming him to our virtual stage.
Thank you, Playtika. I will now share my screen. Hello, my name is Hugo. I'm a senior data scientist at Playtika Research, and today I will talk about efficient text classification with eco-state networks. So this is a joint work with Jérémy Cabessa, Hichan Kim, Yves Lamonato, and Yari Bley. So for anyone that has been working on NLP in the last few years, you might have noticed the models are getting really heavy. And this is because, as we know, transformers have really changed the game in NLP, and they have facilitated breakthroughs in many tasks. And now they're starting to be applied even to computer vision. But the models have grown really dramatically in size. If you take a few of the recent models and you look on the y-axis at the log number of parameters in millions, you see that BERT that came in 2018 had 110 million, GPT-2 the next year had 1.5 billion, Turing NLG 17 billion, GPT-3 175 billion, and the latest model from Google, the Google Switch, has 1.7 trillion parameters. So this is quite dramatic. And now let's define text classification, which is the task we are interested in. So this is really the bread and butter of NLP work. It is simply about taking some text and predicting the class of the text. It could be the topic, it could be things like sentiment. And here at Playtika, we use text classification a lot, especially in projects relating to customer support. For instance, you could be trying to do triage of incoming customer support tickets. You could be trying to identify the purchase receipts of players. And also you could be trying to analyze player sentiment, which is what we do. We analyze it and we aggregate it. And typically, really for text classification, the pipeline that most people would use these days is they would take a pre-trained BERT model, which is still a pretty big model with over 100 million parameters. And they would cut the head of the model, and they would then put a classification head and fine-tune it on a specific dataset or a specific downstream task. However, transformer models such as BERT are not always easy to use in production for several reasons. First, the training can be really slow, so it could take up to 10 hours or even more sometimes to fine-tune them on a task. And also the models that it generates will be very heavy, frequently more than 1 gigabyte, which means if you want to use these models in production, you need to have really good hardware. You might want to have even GPUs in production. So this is quite a lot of effort to deploy them. Now, how about efficient text classification? So what we do is we simply took a step back and we asked ourselves, can we train accurate models, but which are still reasonably light, which will train fast enough? So in this presentation, we consider a method called eco-state networks for this task. And they fall in the category really of reservoir computing. And they are a specific kind of recurrent neural network. So because they are recurrent, it makes them really suited for sequential tasks like text processing. The benefit of this method is that they contain very few learnable parameters. And as a consequence, they can potentially train very quickly, even on a CPU machine. So now let's look at the high-level architecture of an eco-state network. You have several components. The input layer. So on the left, you see the input is in green. This is associated with a matrix, which is a WIN. Then you have a reservoir. This is the part in the middle. This is a reservoir of neurons, which is random, recurrent, and highly sparse. And then you have an output layer in red, which is associated with the matrix W out. So the interesting thing here is that both WIN and WRES, the reservoir matrix, are random, so you don't need to train them. and only the output layer is trained. So let's look at how you initialize an ecostate network. So this matrix WIN is not trained, as I mentioned. You simply sample it from a uniform distribution. So you need to choose a hyperparameter A, which is the input scaling. Then you sample the weights of the matrix from uniform distribution of -A and A. Then when it comes to the middle component of the matrix, the reservoir, it's again not trained. You sample it from a uniform distribution between -1 and 1. And an interesting property is that the weights are randomly set to 0, so that you can achieve a certain target level of sparsity. Usually people use, and we also use, 99% sparsity. So in the end, you actually have to store only a few weights, even though WRES can be quite large. It could be a few thousand by a few thousand, but the actual number of non-zero weights is very small. So one particularity is that to get the ecostate property, you need to make sure that the spectral radius of the matrix rho is smaller than 1. So this spectral radius is defined as the largest of the absolute of all the eigenvalues of the matrix. And then you have your matrix W out, which is the only matrix that is trained by the algorithm, usually using a simple ridge regression, which is nice because you don't need to do any kind of slow or costly gradient descent over the weights. So now let's look at the dynamics of an ecostate network. So here, just a note, we consider only leaky integrator ESNs. And these are the equations which describe the dynamics of the ESN. So you see here, U is the input. So the input at time step t+1, which is in green here, will be projected on the WIN matrix. Then you add it with x of t. X of t is simply the output of the reservoir at the previous time step, which you multiply again by the matrix of the reservoir, WRES. This way you have the recurrence aspect of it. You sum these two components, and then you apply a nonlinearity. Usually we use a hyperbolic tangent. And then what you do is you can use a leaking rate in order to remember more or less information about the previous outputs of the reservoir. So the idea is that you do an interpolation between the current output of the reservoir times alpha, the leaking rate, and also between the previous output of the reservoir. So a high leaking rate would mean you are forgetting a lot of the old information. So if you do that, this number will be small, and then you would be using the current output more than the previous output. Conversely, a low leaking rate means that you would be remembering more the past and less the current input, yes. And finally, to go from this to the output, you multiply this by the W out matrix, which is the one that is learned, and you eventually apply nonlinearity. Here we only use the identity function. So that's how you get your output in red. Now, in terms of features that we use for training our ESNs using on NLP tasks, we use embeddings, which are a way to represent text in a dense way. So we have two kinds of embeddings in our toolkit. Either we can use static embeddings. One example is GLOB, which is a very typical standard algorithm. It's an embedding scheme which is based on word co-occurrences. And it gives you a 300-dimensional representation for each word. So the benefit of using that is that it's very, very fast because you only have to do a matrix lookup to find the embedding of a word. But a drawback is that it's not so powerful. On the other hand, you have dynamic embeddings. For that, we can use, for instance, a pre-trained BERT model, but only as a feature extractor. So we don't do any additional training. And in this case, the sentence is fed into BERT, and the embedding for each word then is extracted from the network. So you get then more contextual embeddings compared to the static version. So this gives us a higher dimension embedding, 768 per word. And of course, this is much slower now because you are not only doing a matrix lookup, you are actually feeding a sentence through a big neural network, but this is much more expressive. So now we've looked at the architecture and the input of the network. Let's look at the way you can train the echo-state networks. So let's assume you have a few texts at T1, T2, T3. These are made up of words. You have W1, W12, and then same for the second text. The first thing you do is you embed this text. So in this matrix here, the rows represent the words and the columns represent the dimension of the embedding. So you see the embedding has dimension NU. So you do that for every text. Here you see that some texts might have more words, some might have less words. So in this case, what we do is we pad the text with extra words so that they all have the same, with extra empty words, so they all have the same length. This is so we can process things in batches to make things a bit faster. The second step is to pass these embedded inputs through the reservoir. So after they go through the reservoir, you get the same kind of matrix as well for each sentence. It has a number of rows equal to the number of words you had as inputs, and the number of columns is now nx, which is the reservoir dimension. So you do that for every text. Again, this text had more words than the others, so that's why it has slightly more rows than the other matrices. And then you need to only keep one vector to represent your text. So you need to merge all these reservoir states into one to find one that suitably describes your text. What we do, and this is what we call a merging strategy, is we simply apply an averaging of all these rows. This gives you one vector of dimension nx, which represents the first text, one vector which represents the second text, etc. And then you can pair these with the targets, classification targets. If you have 3 classes, this vector will have a dimension of 3. The final step is to apply your learning algorithm. Here we use ridge regression. The nice thing about it is that it has a closed form solution, so it's very fast. And you might have noted that although we are doing classification, we use a regression technique. It is because with ESNs, you don't want to do gradient descent. So even though we could use logistic regression, we want a closed form solution that computes very quickly. So we use this technique instead. Now, in terms of our data sets, we've evaluated the proposed method on several data sets. So the first one is very standard. It's TREC, which is about question classification. You can either use 6 or 50 classes. You have around 5,000 sentences in train, 500 in test. The second data set is SST2. So it's a binary classification problem on sentiment, yes, on movie reviews as well. This time you're interested in predicting the sentiment of phrases, so parts of a larger sentiment tree. It's a bigger corpus. You have 67,000 phrases in training. You have a small validation set, and then you have around 2,000 in test. Then we use INDB. It's a binary classification problem, very standard data set again, movie reviews. It's a big data set, 25,000 text trained, 25,000 in test. It's balanced, so you have as many positives as negative examples. And then we used a dataset called AG News, which is about topic classification of headlines. Big data set, 120,000 sentences in train, around 8,000 in test. So whenever there is no validation set, we split the train set ourselves for parameter tuning. So the first thing we can look at is the effect of the input embedding. We want to understand how does its quality affect the performance of the echo-state network. So what we do is we use default hyperparameters for the ESN. We set the reservoir size nx to 1000. We set the input scaling to 0.5, the decay rate to 0.8, the spectral radius to 0.6, and the regularization coefficient in ridge to 1. Then we measure the accuracy on the test set of IMDb. And what we see is that clearly, when you use better and better embeddings, the performance goes up, the accuracy goes up. So for instance, if you look at GLOVE, which is the static embedding scheme we used, when you use a GLOVE that has been trained on 6 billion tokens versus 42 billion or 840 billion tokens, when you use more and more refined embedding scheme, the accuracy goes up. Also, what you see is that the best accuracy is obtained with BERT embeddings. So in this case, indeed, you are using dynamic embeddings that are based from, they come from the BERT net. So these are very accurate embeddings, very rich. They give you a lot of context. So we do see a big increase in accuracy when we use them. Now, if you look at more detailed results, we can compare for track 6, track 50, and IMDb. If you compare an ESN that uses as input GLOVE versus an ESN that uses as input BERT, you will see that by using BERT, the dynamic embedding, the accuracy goes up quite significantly in each case. And you see, yes, BERT gives really better performance, but this is a trade-off always. You get higher accuracy, but you have at the expense of the training time. So here you see with GLOVE, it took around 3 seconds to train. With BERT, it took around 16 seconds to train. Here, 7 seconds against 20 seconds. And here, 38 against almost 200 seconds. So this is 2 to 6 times slower to use a dynamic embedding like BERT, although you get higher accuracy in this case. Now, what we can do, what's interesting, is to look at the effect of the reservoir size on the performance. So the reservoir is really the size of this WRES matrix, this square matrix. People usually have studied all sorts of reservoir sizes, ranging from 50 or 100, but you can increase this size to several thousand. So what we do here is we use BERT embeddings. And to train our ASN, we do hyperparameter optimization using Bayesian optimization. And we also introduce baseline in blue here, which we call the ridge regression baseline. So this one is using the same input as the ESN. It uses the same embedding, but instead of going through the reservoir, we simply average the inputs and go straight through the ridge regression. So we completely skip the reservoir. And what we see is that in track 6, for instance, the ESN already beats the baseline even with a small reservoir of 500. But as soon as you start to increase the reservoir size, the performance really goes up. For track 50, with 500, we are under the baseline. But as soon as you start to increase the reservoir size, again, we see the same shape. If you look at other data sets, you will see the same thing for SST2, for IMDb, for AG News. On each data set, clearly, when you increase the reservoir size, you do increase accuracy as well. Now you can look at performance in more details. So here we look at the ridge regression baseline. If you compare that to the ESN, you see clearly that the ESN with a large enough reservoir will always beat the ridge regression baseline. So 95 against 89, 84 against 75, etc. We also introduced a bi-ESN, which is an ESN with that feeds the sentence in both ways. In this case, it also gets similar performance, sometimes better, sometimes slightly worse, but it's the same ballpark. And what we did, we also compared our ESN to a very standard method in the literature, which is the bi-LSTM. And we see that on some datasets, the ESN beats the bi-LSTM. On track, for instance, get higher scores. But on larger datasets, like SST2 or IMDb or AG News, the bi-LSTM does better. Of course, we see that BERT is really consistently better. This is expected. These are the results of BERT in the literature. We've also reproduced them. We got slightly lower scores because we didn't always know which hyperparameters the researchers were using in their papers, but we see that consistently BERT is the best, but it's a really much slower model. And when you fine-tune it, it has a lot more parameters than the model we proposed, the eco-state network. Now it's interesting to look also at training times. So on the x-axis, we've put all the models we evaluated. On the y-axis, we've put the training time. And you see that the fastest method consistently on every data set is the ridge regression baseline. This is expected. This is the simplest method. It's only a linear model after all. Then it's the ESN. Then the BioSTM is always getting quite longer. And the BERT fine-tuning is always the slowest by far on every data set. So ESMs are really significantly faster than BioSTMs and BERT fine-tuning on every data set. Of course, the ESNs are slower than the RR baseline, but they are always in the same they have comparable training times, and they are always more accurate. Now, let's look at training times in more detail. If you compare the ridge regression baseline to the ESN, the ridge regression baseline is always faster. Here, it's a factor of two times faster. It's around the same here. Not always. On larger data sets, this changes. The ESN is slower a lot, but if you compare that, and that's a really interesting result, to BioSTM, to BERT, we see that ESNs are really clearly significantly faster than the BioSTMs and BERT fine-tuning. So they are slower than the ridge regression baseline, but they are also a lot more accurate. So to conclude this study, we've seen that ESNs achieved really decent results with very fast training times. This is because there are very few trainable parameters compared to larger models like STMs or BERT with fine-tuning. So they do compete in terms of performance. They are on par with the level of BioSTMs, but they really contain orders of magnitude less trainable parameters. From our experiments, we see that they are 5 to 10 times faster to train. So that's interesting if you are constrained by time. Of course, we saw that they are less accurate than BERT fine-tuning, but they are 34 to 212 times faster to train. Also, interestingly, this translates into less energy use. So that's a positive for the ESNs. In terms of next steps, so the merging strategy that we used is simply taking the outputs of all the reservoir states and really averaging them out. So this seems to work well in practice, but we could think of much more refined merging strategies. You could think of weighted averages, or using weighted averages where you put more weight on more interesting words, or words which are more related to sentiment, for instance, if you're working on a sentiment task. Also, you could use attention mechanisms, which is something that has been used in transformers. So all these things could potentially increase the performance without increasing the training times too much. Also, we noticed that ESNs tend to do better on smaller data sets. So it would be interesting to study the performance of ESNs in this few shot setting. It could be interesting to even go to really settings where you only give a few samples of each class and evaluate the method against other few shot learning algorithms. And finally, one last thing we could try is to study the effect of the reservoir size in more detail. We saw in our results that as you increase the reservoir size, the performance goes up. Of course, you have a trade-off again. You increase the training time, but not that much usually. So you can see that there does increase, but it would be interesting to understand what is the maximum attainable accuracy that is obtainable. So more study would be needed to understand the behavior of the reservoir and its impact on accuracy in the limit. That's it. Thank you.
Wow, thank you so much. That was amazing. Thank you for sharing with us today. I know this virtual audience is giving you a huge virtual round of applause. We appreciate your time today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.